I was part of a project where we had to do a major refactor of existing product. This refactor took about 18 months or something like that. We did the refactor with a team of 30 people, and we basically took an application that used to be a standalone application and moved it to cloud, like made it a service as a software kind of application. So as a QE, because I'm a QE, I wanted developers to basically enjoy the ride, like enjoy the whole project for the 18 months, so they don't find themselves like throwing up during the ride, right? And in order to do that, I decided to look into the safety net that we had, or we rather were thinking that we had at that point of time. And when I'm talking about safety net, I'm talking about tests, like automated tests that we used to have for the project, for the application. I'm not sure if you are aware of this symbol, right? Like if you heard about test pyramid, like there is this concept that you need to have different types of tests for your system on different level, and have more tests on the lower level than you have on the higher level. So you should have as many unit tests as you can, and then move upwards to the system level tests and have less of them. And when you look into our automated tests and how much tests we had for the project, it looked pretty good. And we basically have this kind of pyramid, and we talk about numbers a little bit further, because like automated testing is part of our developers' DNA. So the funny thing is that although I am quite an engineer, I don't really test, and I don't really automate tests. It's part of developers' responsibility. I'm just there in the company to teach them how to test, how to implement automated tests, and how to explore application. It's their job to implement automated tests. So we have pretty good coverage. We have pretty good numbers when it comes to automated tests, and we have this mythical pyramid. So we have good numbers of unit tests, integration functional tests, REST API tests, and WebDriver tests. So you could say that, okay, if that's true, and we have like those automated tests, what I was looking for, like clearly we have enough coverage. Clearly we have the safety net that I was looking for. So we shouldn't be afraid of the refactor. Okay, and here I'm going to stop for a moment and talk about this presentation. So what you're going to hear about is not really that much about test coverage and tools, but I'm going to talk about risk. And I'm going to talk about tests that you must have, but you probably don't. And also I'm going to talk about tests that you might have, but you don't necessarily need to have. Like you can basically remove them or skip them. I'm not going to talk about code coverage, like what it is. I assume that you all, at some point of your career, work with a code coverage, use some kind of tools, read some kind of reports. I'm not going to cover that, and this also means that I'm not going to go like through all the tools that are possible, that are available. I'm just going to expand on the idea. But before I do that, and before I talk about the journey and how it evolved, I need to show you a few things. Like, not sure if you ever used this tool. It's Clover, developed by Atlassian. It's basically one of the tools that you can use to generate a code coverage report for your Java or Groovy application. And like nothing fancy here. You have some basic numbers. Like in this example, you have like 70% of code coverage, right? For the application that was used here for the report. What's nice about this tool is that it also gives you information about tests that go through particular line of code. And it was pretty crucial for the research that I did to understand the safety net that we had for our application. So you can click on a single line and see all the tests that exercise that line. And it isn't limited only to unit tests. It can show you other types of tests, also tests that are executed from different JVM than the JVM that your application is running on. So it was pretty cool to have that tool and have that information. The problem is that in order to generate this report, you need to spend a lot of time. First, you need to instrument your code. Second, you need to generate this HTML report for your code. And if it's becoming a problem when you have like a project with hundreds of thousands of lines of code, and like the number of tests is over or similar to hundreds of thousand tests, right? Like to run all those tests against instrumented application is very time consuming. And also generating this HTML report is also, in that case, very time consuming. So I had to improve the tool a bit, and what I come up with is a database that contained all that information that I originally had in the HTML report. But instead of generating beautiful HTML report, I decided to just scrape the data from like 100. Yeah, it was probably like 50 different reports that Clover generated for me for different types of tests that we had. Also split into batches and to put that data into database. And this is the part of the outcome. So part of what was in the database. I had information about the class names that were covered by tests, information about methods, information even about lines that were covered by particular test type and particular suite and particular test case. So that kind of database contained information about whole application source code and also about all the tests that were exercising this code. So it's pretty good data, and what this data told me is that the coverage is somewhere between 80 to 99%. And when I'm saying coverage, I'm talking about statement coverage. And this is another thing that I'm not going to talk about. Like, I'm not going to cover all different types of coverage that are out there. I just focus on the statement coverage as the one that I'm going to talk about. But this was the information that the database gave me, that we have around 80 to 99% of code covered. And like, what this information really tells you, like, is it good enough to have 80% of code covered? Should you aim to have 99% of code covered? Maybe you should have like 100% of statements covered. And that was definitely a problem that I was struggling with, and I couldn't really find the answer. So I was looking for some low-hanging fruits, right? Maybe there is some kind of information in the database that I can use to improve things, right? Maybe it won't necessarily answer this question whether 80% is good enough, but at least I will be able to improve the code a bit. And I decided to look into packages, and there are like hundreds of packages in the application that I was working on, and maybe there are some packages where the code coverage is not that good enough than in any other packages, right? And maybe we have package that is not covered by any test. Maybe it's covered only 10% of that package is covered by tests, comparing to other packages where this coverage is higher. Okay, and I'm going to present a lot of those. So hopefully you won't get scared and run away. What you see here is our application, the application that I was working on. It's like visual representation of the code of that application. Like the whole square, the big square is the code. Every single rectangle that you see in the square is a single Java package. And there are like hundreds of those. And when it comes to the area of those rectangles, they represent different things. Like in this case, they represent missing test coverage. So just comparing like those packages between each other, I probably wanted to like find a single rectangle for which the area was greater than any rectangle in this big square, right? Because this would tell me that there is a package where code coverage is not that good enough and is lacking comparing to other packages in the application. And as you can see, there aren't such packages here. Like they are very similar when it comes to size. They are very similar when it comes to missing test coverage. So at that point of time, I probably could stop and just say that, okay, we know that the coverage is around 80 to 99%. I can't find any package that we need to improve, because I can't really ask developers, okay, we need to now implement tests for every single package. We know where and how many tests we are missing. So now let's spend half a year implementing tests for those missing places. Like that wouldn't be feasible. But I decided to do a bit of research and spend my innovation time looking into the information that the database gives me, and also looking into different other sources of data. So I started looking into lines of code, like those statements that are missing tests. If you say that like 80% of your code is covered with tests, it doesn't sound that bad, right? Because like, oh, it's a great number, like 80%. It's definitely more than 10%. It's almost 100%. But if you change your perspective and look at the number from lines of code, and let's say that your application is made of 500,000 lines of code, right? 80% is still okay, right? Because it's like 400,000 lines of code. But 20% now means that there is 100,000 lines of code not covered with any tests. So the question now is, what are those 100,000 lines of code responsible for? Like, what is their purpose? And this was the answer that I wanted to find. Like, what those 100,000 lines of code do, and should we have tests for those for any of those 100,000 lines of code? So, because I'm a quality engineer, I'm looking at everything from a risk perspective, and you probably all know what the risk is. It's like probably this is like the simplest explanation. It's just probability times severity. In other words, is the frequency of something unfortunate happening, and the value that you're losing when it happens, right? So I decided to look at the lines of code from the risk perspective. And what does it mean? So let's first look into the probability part of the equation. I used Git and check log information for all the files in our application repository, right? So the good thing is that whenever someone decides to make a change in any of those files that are making out our application, they are putting Jira issue keys in the message. And this really helps because you can then find Jira instance, that is where this issue lives. And yeah, we have like dozens of those. So it was like a challenge to find the right Jira instance. But once you are able to find the Jira instance that you are looking for, you are able to find the issue ticket, right? So you can tell which issue was related to fixing a bug, and which one was related to like addressing some technical task, story, etc. And I was after finding how many bugs are fixed for a given file, right? So I was basically after the number of bugs per the number of days that I was analyzing, and it was like 90 days in the first try. So I was looking for the number of bugs per 90 days period of time for every single file in the source code. But we know that bugs are not equal, right? So there are small bugs, bigger bugs. Like you can find something during development and you decide to create issue in Jira to track it. And it's not that big a deal if you find it as a developer or as a QA. But if your customer finds a bug, then probably it's like a big thing. It's considered an incident. And I tried to include that into my analysis and started classifying bugs by like different characteristics, like where this bug was filled in what kind of Jira instance. Was it a public Jira instance? Was it raised by customer, by user, or was it raised by development teams? Also included like this information about priority, severity, this kind of stuff, and decided to give every single class of a bug a score. So the number of bug points that every single bug can have. And once I had that, I derived another metric, which is basically the number of bug points per number of days that I was analyzing. So what you see here is how the code looks like, how the packages in the application look like when it comes to how often change is committed to them and how often there are bugs in packages. And you can see that there is like a correlation between how often we commit to how often there is a bug in source code, right? Because you have this ping package here, which is like takes majority of the whole square of the whole application, which basically means that we are committing to this package more frequently than to any other package in our application. And on the right side, you also see that this package is also taking like most of the space, and it means that we are fixing more bugs there than in any other package. So you could conclude that there is a linear relation between how often you commit to how often you fix a bug, right? Or there is a bug to fix in code. But is it true? Like, let's say that we want to define this bug probability. So this first part of the risk formula, right? And this bug probability will be the number of, or the bug score, or the number of bugs times commit frequency. And this is the result of the. This is how the application look like when you consider this metric, so the bug probability. And as you can see, the ping package is no longer here, and it basically means that there are packages to which we do not commit that frequently, but when we do commit, it's more probable that we will commit a bug. So, for instance, this blue package basically tells me that if someone is making a change there, it's more likely that this change will cause a bug than if that person would commit to any other package in the application. So that was like first lesson learned. We probably need to look as developers and as QAs for changes to any of those packages that are taking more space into the whole square than any other packages. And I don't know, like come up with more testing or some other risk mitigation techniques to avoid bugs. Okay, so that was the probability part of risk. Now let's look at the severity, right? So the lost value. So you can consider. I mean, it all comes to how you are going to model value. I decided to model value by looking from two perspectives. Perspective of a T-shirt, basically perspective of a developer from my team, from the team that was refactoring the application, and perspective of guy in the suit, so business, right? Like what product managers care for. And if you consider value from the T-shirt or developer perspective, what you can define as valuable is something like that. Let's say that you have like a simple class, right, with a simple method. And this class and this method is called by another class, right? So depending on how many dependent classes you have, that valuable you are, right? And you can analyze that by just inspecting your code in IDE and see how many usages there are of a particular method or of a particular class, right? And say that if there are more usages, then this part of code is more valuable to a developer. And I did that, analyzed the code, and found out that there are packages that are even responsible for 1/3 of references in our application, right? So if someone changes like this green package, for instance, code of this green package and introduces a bug, this bug will affect 1/3 of application, right? So this is definitely greater loss in value comparing to any other package like from the top right corner, for instance. Okay, what about business perspective, right? Like what business value? Yeah, I mean, it might be a cliche, but we value happy users and happy customers, right? And we are getting those happy users and customers by providing them tools, right? So now everything comes to what is a tool, what is a feature, what is a functionality. It still comes to modeling that. And I decided to model in particular ways. So I will talk about that a little bit further. But let's say that your application is just a collection of features, and those features are used by different users, right? Like different personas, etc. And you may have users that rely on 2 crucial features in your application. You may have a user that relies only on one features, and you basically can derive from that information that this feature in the middle is probably the most valuable one, right? Because it's used by 2 users in this example. And how we know that what kind of features we have and how they are used? Like we track events. We have access logs, we have analytic events, so we know how often something is used and by how many users. Like the simplest data source that you could use is access logs. And let's say that in the most simplistic way, every feature is represented by a REST resource, right? So every REST resource represents a feature. So you can analyze now access logs to understand how many users, how many customers depend on every single feature. And this is the approach I took. And what you see here is all the features that we have in our application, every single REST resource that we have in our application, and on the left is the number of requests made to those REST resources, and on the right the number of unique users. So probably depending which metric you will choose, whether it's a number of requests or the number of unique users, you will be interested either to focus your attention on this brown feature or on this bluish one, right? And I decided instead of looking into the number of requests, look into the number of unique users, right? So I'm interested in features that are used by most unique users, comparing to any other feature in my application. And the problem is that now we are talking about features, right? Like in the most simplistic definition, let's say the REST resources, right, in our application. We don't have information about coverage of REST resources. We don't have information about coverage of features. Like this database that I've shown you in the beginning was only telling the story when it comes to code, like what code is covered by tests and what isn't. So how can you move from feature level to code level? That was a problem that I faced, and honestly, it's not that hard to find the connection. Like every single REST request that you make is handled by some code, right? So you have like this is probably another simple class that has a handler responsible for responding to a REST request, right? Of course, this isn't how the code looks like. This isn't how the code looks like in our application. It's more complex. And, but you still can use that as an example and apply it to real application. And this is what I did. And what you see here is a tree of calls made on every single REST request, right? So there are like every single level is a call to a class or to a set of classes. The next level is what classes are called from those classes, etc., etc. And depending how many layers there are, your tree will grow to such proportions. Like this is probably the most the very basic resource that we have in our application. But still, you see how many classes, how many methods are involved, because every single node here is a method basically that is called on a request. But now when you have that information, and when I had that information, I was able to overlay the number of users requesting resource with packages, right? Because we have that mapping. And what you see here is packages mapped by the number of unique users that depend on them, depend on the code that is in them. So now when I got that information, I was able to compute risk, which is a bug probability times the dependent methods and dependent unique users, right? Or maybe I applied a bit different equation, but after all, I was able to come up with such a representation of the application, which basically was telling me which package is more risky than other package. Okay, question. Yeah, I found all implementations, and this, yeah, that was the problem. Yeah. And this is a representation of the application when it comes to the risk. And every single rectangle is a package. The greater the size of the rectangle, the greater the risk is. Okay, and now when I had that information, and I decided to do something more. One could say that coverage is a function of risk, right? Like this is clearly what I was doing. And if that's true, like coverage is a function of risk, you could say that if the risk increases, if the risk is 1, you want like the 100% coverage. You want all the code covered. But at the same time, you can say that if the risk is 0 or is close to 0, you don't want coverage for that code, right? Because why you bother like testing that code? You are just spending time running your tests in your pipeline for code that isn't risky. Like either no one uses it or there aren't any evidence of bugs in that code. And this is the test coverage efficiency that I introduced. And I decided to look into the application and see if we are following that. Like, do we have more tests for the code that is more risky? And do we have less tests for the less risky code? And as you can see, it's the case. Like, as the risk increases, so does the coverage. So that's pretty good. I mean, still, it's not 0 for the less risky or no risky parts of the application, but it's lower than for the high risk code. Okay, so now get back to the original question: is 80% good enough? I still don't know the answer to that question, but I am able to rephrase it. And the question that I now can ask and answer is: are there high risk methods with 0 statement coverage? And yeah, I was able to find 10 methods in the 95th percentile when it comes to risks. I was also able to find all the methods without 100% statement coverage that are the most risky ones, right? And found out that there are like 50 methods that are in the 95th percentile of risk. I was also able to find whether there are integration tests or those high-level tests for the most risky part of the application, because I was keeping the information about test type in my database and found out that there are 200 methods like that are missing integration tests. Analysis helped me find that code unused by any other code that I don't know why we were keeping in the application. This analysis also helped me find dead features that no one is using based on the data that we have. And because of that, there are also dead tests that are probably like included in this test pyramid, but aren't really useful and are just taking time, execution time, and slowing us down. And another thing is that when I created that database, I was also able to use that database to, in a more smart way, decide which test to run on a change. But it's time out, and if you want to ask me about that, just ask me after the presentation. That's it. Thank you. Have any questions? Go on.
Did you extract all the schemas? Do you have a tool or something?
Yeah, I mean, I spent some time just creating a tool that extracted data from different sources. The funny thing is that I used a tool that was developed separately because we also, when we were doing this refactor, we also implemented a tool that was extracting meta information from code, like all the relations between interfaces, implementations, etc. And we used that initially. We used that tool to find problems that we need to fix in order to make the application like software as a service kind of application. Like we didn't want to have any sessions, etc. And we needed to create a tool that will automatically spot any use of session in the source code. Because it's not possible to find that manually. And I basically use that database to find the relation between those annotations, those jersey annotations, and the code. Yeah.
So it's an inside tool?
Yeah, it's an inside tool. Yeah.
Did you do the analysis before the refactoring, or
no? The analysis was happening along the refactoring. So it's not that we were deploying something as the refactor went. So yeah, still this analysis was useful, and we improved coverage in the most critical parts of the software.
Okay, I'm just wondering how that worked, because if today you had the package X with a high risk and
yeah, I mean,
and then tomorrow they changed that package
yeah.
and split it and so on.
Yeah, I probably had to say that this was only one time thing. Like this was part of a research, part of the innovation time. I didn't know how much time would be needed to analyze the source code, combine data from different sources, and we find out that it's just taking too much time. Like just combining everything took like 16 hours or something like that. So you can't really have that analysis done for every single change, right? For every single commit. And it's even not feasible to have that analysis done for every on weekly basis or something like that. So we decided to just do it once. But it's not that we didn't use that information in any way, because we created the database of tests to source code. And we are now using this database to do something called test impact analysis. So depending on what files are changed, we are looking into the database and finding only the tests that should be run for this particular change. And this is helping us to save, I don't know, like 80% of time that we used to waste running all the tests. Yeah. Okay.
Could you talk a bit more about the factors that were put into the bug score calculation?
Oh yeah, so the most important factor was the type of instance. So we have different Jira instances, and most of them are for the development purpose. So we know that no one else than developers have access to those instances, so no one else can raise a bug or incident. So that was like one thing. So basically look into the type of the instance. Is it a public one? Another thing is like checking who raised a bug. Was it someone from inside the organization or was it someone outside the organization? We also have a special instance that is used only for the critical type of incidents. And for those type of incidents, we have like various custom fields in Jira that decide what's the severity of an incident. And basically, I was using that information to increase the score of a bug if this kind of bug happened.